Hello everyone, my name is Dhruv Agrawal and I am from group number 22. My team members are Mudit Mangal and Pulkit Garg, and today I am going to present to you all a computational geometry project. Firstly, we have implemented a traditional art gallery problem, that is, the guards have to be placed on the vertices and the whole interior of the polygon have to be visible. And there is a well-known theorem for that the number of guards that are sufficient to guard any polygon with n edges is lower bound of n by 3. And in our system we have not only implemented the traditional vertex guard solution, but we have also extended it to a more advanced version, the mobile guard problem, where the guards can move along the edges of the order diagonals of the polygon. This allows us to reduce the number of guards in many cases. So first let's have a simulation run of our code. So running our program, first it will ask for the input value of n, that is the number of sides we want in a polygon, and will generate a random polygon based upon our input. So first let's have number of edges as 8. Entering that, first in the first step a random polygon will be generated. In the second step the trapezoidal edges and pivots will be seen. In this we have used the sweep line approach for trapezoidization, and this step is important for the pre-processing of making monotone polygons and eventually triangulating it. In the next step we introduce the diagonals of these trapezoids. Yeah, in this the monotone polygon, if any vertical line intersects it at most 2 points, this property is essential to enable the efficient triangulation. And in the fourth step, that after partitioning we now have smaller monotone polygons. Each of these will be triangulated independently. That will do in the fifth step, that is, each monotone polygon is triangulated. Triangulation is the foundation for both the algorithms that we have implemented, that is the traditional AGP and the mobile guard problem. In the sixth step we have performed the three coloring. This is done by constructing the dual graph of the triangulation, and we can see that the blue number of vertices appear the least number of times, and hence we will place our vertex guards at these blue points, and we'll need two vertex guards in this situation. We can also verify that we had taken 8 n as 8, so it is bounded by 8 by 3, that is lower bound of 8 by 3, that is 2. And in the last step, that is the 8th step, we have the main extension that we have done. Instead of static guards at vertices, we allow mobile guards that can move along the polygon edges or diagonals. Theoretical guarantee here improves. Only a lower bound of n by 4 mobile guards are sufficient. This algorithm we have implemented using this research paper. There is a whole lot of lemmas that they have proved, but at last this is the algorithm that we have finally implemented. In this, we first compute a triangulation of the polygon using Chazzel's linear time algorithm. We then maintain two sets of diagonals, that is D3 and D4. What D3 represents is the diagonals cutting 3 edges of the polygon, and D4 diagonals cutting 4 edges of the polygon. In each iteration, we pick one diagonal, split the polygon, and update D3 and D4 in constant time by checking nearby vertices. This process continues until the polygon reduces completely, yielding the set of diagonals edges along which mobile guard should be placed. In and Yes, this is the algorithm, and you can again see that the mobile number of guards we are getting as 2, which is again bounded by the lower bound of n by 4, that is 8 by 4, that is 2, and we are getting 2, which is less than or equal to 2. And here we can see that we can place one guard at this edge, and one guard can be placed at this diagonal. Okay. And our GUI also allows us to adding custom points manually. So instead of random graphs, we can just construct any polygon shape by clicking points on the canvas and rerunning the algorithm. Okay. So just to show scalability, let's quickly run for some more values of n, and let's have analyze their outputs as well. So for previously we had taken 8, now let's take as 15. Now we have taken 15, and again the same steps have been generated. Like this is the polygon, then the trapezoidal boundaries, then diagonals are introduced, then monotone polygons, then they are triangulated, then three coloring, then vertex, then mobile guards. Again you can see the results that 15 by 3, that is 5, and 4 we are getting 4, that is less than 5, and we and in this case 15 by 4 is and its lower bound is 3, and we are getting 3, so we can verify that our outputs are correct. Now let's quickly have a demonstration for some higher values of n. Let's suppose we take 25. In this, a polygon is a bit complex, but again we can see the output, like these are the vertex guards, these are the mobile guards, and in this case also you can verify that the count that we are getting are according to the theorem specified. Okay, now let's have even higher than 25, let's have 30. Okay, and we get an even complex arrangement, but still our algorithm works correctly and we are able to get the output. And at last, let's have an illustration for n is equals to 40. So you can see that although we cannot see each and everything explicitly, but we can see that the algorithm is working perfectly fine and we are getting our output as expected. Okay, now let's have a brief look at our code structure as well. So basically, this is the main.py, that is the entry point, handles GUI, runs the algorithms, and generates visualizations. This is the dcel.py. This implements the doubly connected edge list, which is the backbone data structure to represent polygons. And then we have the monotone partitioning, which implements the monotone partitioning of the polygons. Then we have triangulation, which handles triangulation of monotone polygons. We have three coloring, which builds the dual graph, performs three colorings, and selects the vertex guards. And this is the our extension implementing the mobile edge guard algorithm. And yeah, that was it. In conclusion, our system not only solves the classical art gallery problem but also extends it to mobile guards problem. And we have provided a full visualization of each and every step, from partitioning to triangulation to guard selection, and making the process transparent and easy to understand. Thank you for your time. Thank you.